Invariance of ratios, and similar triangles. Welcome, everyone. To begin our lesson today, let's take a moment to reflect on what we have covered in our previous sections. Up until now, we have been defining our trigonometric ratios, like sine, cosine, and tangent, based specifically on the lengths of the sides of a right-angled triangle. Now, as we move into this new concept, a very natural and important question arises. Suppose we are looking at two different right-angled triangles. Both triangles share the exact same acute angle, but one triangle is much larger than the other. In this scenario, would the trigonometric ratios remain the same, or would they change as the triangle grows? The answer is a definitive yes. It is crucial to understand that the value of a trigonometric ratio depends solely on the measure of the angle itself. It is completely independent of the actual physical lengths of the sides of the triangle. Whether the triangle is tiny or massive, if the angle is the same, the ratio is the same. In mathematics, we refer to this fundamental property as the invariance of trigonometric ratios. In the next few slides, we are going to use the concept of similarity to prove exactly why this is true. Understanding the concept through similarity. Now that we've established the big question, whether the size of a triangle actually changes its trigonometric ratios, let's dive into the why. To understand why these ratios remain constant, we need to step back from trigonometry for a moment and look at a fundamental geometric concept called similar triangles. So, what does it actually mean for two triangles to be similar? It's not just about them looking the same shape. Two triangles are mathematically similar if they meet two specific conditions. First, their corresponding angles must be exactly equal, and second, their corresponding sides must be in the same proportion. Think of it like a photograph. If you enlarge a photo, the objects in it look bigger, but their proportions and shapes remain unchanged. When we are working specifically with right-angled triangles, as we have been in our previous lessons, we don't actually need to check every single angle or side. Instead, we use a shortcut known as the AA similarity criterion, which stands for angle-angle. The AA similarity criterion states that if you can prove that just two angles of one triangle are equal to two angles of another triangle, then you have enough evidence to conclude that the two triangles are similar. This is a powerful tool, and as we are about to see in the next few slides, it is the key to proving that our trigonometric ratios never change, no matter how large or small the triangle becomes. Step-by-step logical proof. Now that we understand the concept of similarity from the previous slide, let's put it into practice with a formal logical proof. To start, let's visualize two different right-angled triangles. We will call the first one triangle PAM and the second one triangle CAB. For our proof to work, we need both of these triangles to have a right angle, and they must both share the exact same acute angle, which we will call angle A. Now, let's move into step 1, where our goal is to establish similarity between these two triangles. To do this, we look at the specific angles they share. First, notice that angle A is common to both triangles. It is the same angle in both triangle PAM and triangle CAB. Second, we know that angle P and angle C are both equal to 90 degrees, as they are our right angles. Because we have identified two pairs of equal angles, we can apply the AA, or angle-angle, similarity criterion. This allows us to mathematically conclude that triangle PAM is similar to triangle CAB. This similarity is the crucial foundation we need for the next step, where we will show how this leads to constant ratios. Step-by-step logical proof continued. Now that we have established in the previous slide that triangle PAM and triangle CAB are similar using the AA criterion, let's move into step 2, where we apply the fundamental property of similar triangles. Because these two triangles are similar, we know that their corresponding sides are in proportion. This is a crucial point. It means that the ratio of any two corresponding sides remains constant across both triangles. Depending on how the triangles are oriented, we can write this as MP over BC equals a P over a C, which also equals PM over B. Now, let's transition to step 3, where we begin to rearrange these proportions to specifically form our trigonometric ratios. To make this clear, let's focus our attention on one specific ratio, the side opposite to angle A divided by the hypotenuse. If we look at our smaller triangle, triangle PAM, that ratio is MP over P, and if we look at our larger triangle, triangle CAB, that same ratio is BC over C. As we will see in the next slide, these two fractions are actually equal, which is the key to our entire proof. Step-by-step logical proof, conclusion. If we look back at step 2, where we established that these two triangles are similar, we know that their corresponding sides must be in proportion. This means that the ratio of the side opposite to angle A to the hypotenuse in our smaller triangle, which is MP over AP, must be exactly equal to the same ratio in our larger triangle, which is BC over C. Moving into step 4, we reach our final conclusion. Since we have already defined the ratio of BC over C as the sine of angle A, it logically follows that sine of angle A is equal to MP over AP, which is also equal to BC over C. What does this actually tell us? It proves that regardless of whether we are looking at a tiny triangle, like triangle PAM, or a much larger triangle, like triangle CAB, the value of the sine ratio remains identical, provided that the measure of angle A remains constant. This is the very essence of what we call the invariance of trigonometric ratios. Now, let's bring our logical proof to its conclusion. Real-world example, the shadow method. Now that we have established the mathematical proof using similar triangles, let's step away from the abstract symbols and look at a practical, real-world application. This will help you see the invariance we just discussed in action. Imagine you are standing outside and you see two vertical poles of different heights standing on level ground. Now, think about a specific moment in the afternoon. At this exact time, the sun's rays are hitting the ground at the same angle, which we will call theta, for both poles. Let's look at a specific scenario to test our theory. Suppose we have pole 1, which is a shorter pole, standing at a height of 3 meters, and it is casting a shadow that is 4 meters long. Now, let's look at pole 2, which is a much taller pole, standing at 6 meters, casting a shadow that is 8 meters long. To analyze this, we will follow 3 simple steps. First, we identify the triangles. If you visualize the vertical pole and the horizontal shadow, they meet at a right angle, meaning both poles and their shadows form right-angled triangles. Second, we check the angle. Because the sun is so far away, we can assume its rays are parallel, which means the angle of elevation, theta, is identical for both triangles. Finally, let's calculate the tangent ratio for both. For our first, shorter pole, tangent theta is equal to the opposite side over the adjacent side, which is 3 divided by 4, giving us a result of 0.75. Now, let's do the same for the taller pole. Here, tangent theta is the opposite side over the adjacent side, which is 6 divided by 8. If you simplify that fraction, it also equals 0.75. Notice how the ratio remains unchanged, despite the change in size. Real-world example, observation. If you look closely at our observation, you'll notice something very important. Even though the second pole is twice as tall as the first one, the ratio of tangent theta remains exactly 0.75. This is the aha moment of this example. It confirms exactly what we discussed at the beginning of our lesson. The trigonometric ratio depends entirely on the angle of the sun and is completely independent of the height of the pole. Now, let's take a moment to reflect on the results we just calculated in the previous slide. As we move to the next slide, we will discuss some common pitfalls to watch out for so you don't fall into the trap of confusing side lengths with these constant ratios. Common mistakes to avoid. First, be very careful not to confuse side length with the ratio itself. It is a very common error to think that if the sides of a triangle grow larger, the value of sine A or cosine A must also increase. Remember what we saw in our shadow example with the two poles. While the actual lengths of the sides are increasing, the division of one side by another, the ratio, stays exactly the same. The size changes, but the value of the ratio is invariant. Second, do not ignore the importance of the right angle. Everything we have discussed regarding the invariance of these 6 specific trigonometric ratios relies entirely on the triangles being right-angled. If you lose that 90-degree angle, the AA similarity criterion we used in our proof no longer guarantees these specific ratios will behave the same way. Finally, watch out for misidentifying corresponding sides. When you are comparing a small triangle to a larger one, you must be disciplined. Ensure you are comparing the side opposite to angle A in your first triangle, specifically with the side opposite to angle A in your second triangle. If you mix up your opposite and adjacent sides, your calculations will not reflect the true similarity. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even students who understand the concept of similarity can sometimes stumble on these 3 specific areas. Keep these points in mind as we move into our final summary. Key takeaways. First, let's remember the concept of angle dependency. As we discussed throughout the lesson, trigonometric ratios are functions of the angle itself, not the size of the triangle. Whether you are working with a tiny triangle or a massive one, if the angle remains the same, the ratio remains unchanged. Second, we looked at the AA similarity criterion. This was the mathematical backbone of our proof. We used this criterion to how that, when 2 triangles share the same angles, their corresponding sides are proportional. This proportionality is exactly what allows the ratios to stay consistent. Finally, let's keep in mind the idea of constant value. For any given angle, theta, the values of sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta are all constant. This remains true regardless of the dimensions of the right triangle you are using for your calculations. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear. I hope this clarifies why these ratios are so reliable in trigonometry. Great job following along today.